Morning, everybody. It's a big pleasure for me to be able to talk to you about remote sensing of glaciers. The most important thing to have in mind when talking about glaciers are two special properties of ice on Earth. First, ice on Earth is very often close to the melting point. Many glaciers on Earth are at 0 degree at the pressure melting point, so very close to zero or at zero. Secondly, in order to melt ice which is 0 degree to water of 0 degree, it needs nearly as much energy as to boil water from 0 degree to 100 degree, actually 80 degree. So you need a lot of energy to melt ice, but it's very close to the melting point. This has consequences for glaciers, for instance. Without these two properties, glaciers would not survive, even not a summer, because it would directly melt, but it takes so much energy to melt the ice that glaciers can survive. The same applies for sea ice. Sea ice would not survive a summer because it's swimming in 0 degree water. So sea ice would not survive without these properties. And the same applies for ground ice. The third type of ice on Earth is ground ice, mostly related to permafrost conditions. Such ground ice, you see a river here as a scale. Such ground ice survives many years, decades, even millennia. This is only possible because of the high energy content of ice, or the high energy needed to melt the ice. On the same time, because ice is often very close to the melting point, glaciers also can serve as a climate indicator because they react rapidly sometimes to climate change, or especially change in atmospheric temperature. So this is the background. So 546 is the outline of my talk. I will give you 5 good reasons to monitor glaciers. I will give you 4 good reasons to do that from space. And I will present you shortly 6 methods for glacier monitoring from space. So first to the 5 good reasons to monitor glaciers. First good reason is global sea level rise. As you know, glacier melt contributes to sea level rise. Sea level rise currently is in the order of 3 millimeters per year, and about half of that is due to glacier melt. Glacier melt of Greenland and Antarctica. About half of the, so 1.5, 1.6 millimeters per year. The global sea level rise is really a global problem, but because it doesn't matter if a glacier melts here or here or here or here, it contributes equally to sea level rise around the world. So this is really a globalized problem. Second good reason to monitor glaciers is that glaciers are in many regions, or some regions, a very important water resource, in particular in the dry season, when in some regions glacier meltwater is the only water supply. This is an image in the Pamir. Actually, this is Afghanistan. And most of the water in this river comes from glaciers. Without glacier melt in summertime, there would be no water, and you will see that this water is used for irrigation. So people would hardly live there without this glacier melt water. So Pamir, Central Asia, is a region where glacier melt water plays an important role. Himalayas, the Andes, but also in the Alps, in the inner parts of the Alps, Valais or so, which are very dry, glacier melt water is very important in summertime. A third good reason to monitor glaciers is that they are excellent climate indicators. Here you see an overlay of 2 images from 1972 to 2007. Because glacier ice is so close to zero, it reacts to climate change. And the IPCC recognizes glaciers as one of the best terrestrial climate indicators because glaciers display the climate change so well. So it's hard to see temperature changes. It's sometimes hard to see changes in vegetation, in ecosystems. But it's comparably easy to see changes in glaciers. So they speak a very clear language. So the only way to get rid of so much ice is to turn the heat on or turn the precipitation down. But in our case, the first one happens. It's not only the present day changes of glaciers which tell about climate, it's also past changes. You all know that when glaciers retreat, they leave behind moraines. So moraines tell us about earlier climate, here moraines. Or glaciers store in the ice climate information. You all have heard about the boreholes, drillings in Antarctica, but also on other glaciers where different atmospheric gases are stored and analyzed. So they also are a storage for climate information, climate change information. A fourth good reason to monitor glaciers is that there are hazard sources. A typical hazard for glaciers are ice avalanches. Ice avalanches usually only endanger the region around the glaciers. This is an ice avalanche from '96 in the Swiss Alps, which luckily did not kill a person, but some were hurt and some cows were killed. But it covered a road, so many people could have died. So ice avalanches are a local problem. One of the most far-reaching glacier hazards are glacier lakes. This is a glacier lake on a glacier which developed some years ago in Macugnaga, Monte Rosa. This lake was very close to burst out, and a flood wave would have destroyed this alpine hut, big alpine hut for scale, and the village or part of the village of Macugnaga further down. This lake here, a typical moraine lake, bursted out earlier in the 70s and actually destroyed a cable car. So glacier lakes are a big problem, as you've heard, in the Andes, especially in the Himalayas. Even if people are not living very close to these lakes, the flood waves can reach hundreds of kilometers. I know a case in the Himalaya where someone told me, yeah, the hydropower plant in the Indian plain was destroyed on a sunny day, and they didn't know why. And then even Nepalese scientists told them, yeah, it was a glacier lake outburst. They didn't believe it because you don't see the glaciers, you don't see the mountains, you don't believe that there's a glacier lake which can burst out. So good reason to monitor glaciers. And the fifth reason, also a good one, that glaciers are beautiful. This is Mount Elbrus. And therefore, in some regions, glaciers also are an important background for tourism. So this is an example from the Swiss Alps. So tourists are attracted by glaciers. And we don't know how the tourism will change when glaciers disappear, for instance, in some regions. So I gave you 5 good reasons to monitor glaciers, and I will give you 4 good reasons to do that from space. One is accessibility. Many glaciers in the world are hardly accessible. It's the Himalayan main ridge between Bhutan and the Tibet Plateau. Actually, I never was here. You see, by the way, that this is a glacier lake which bursted out sometimes. So I created this debris flow. But colleagues have been here, and they told me to come here takes about 2 weeks of walking from Thimphu, which is the capital of Bhutan, and you cannot fly to Thimphu, so you have to take the bus to Thimphu and so on and so on. So it's obvious that you cannot do research on these glaciers, on a large number of glaciers here from ground. You can go to 1 or 2 glaciers, but that's it. Secondly, glaciers are sometimes at very unsecure places. This is an image from the International Space Station from the Russian Caucasus. Oh, actually not the Russian Caucasus. It's the border between Russia here, South Georgia, and Chechnya to the left. And actually this was the source of a big ice avalanche which rushed down here and killed 140 people some years ago. And I worked there also in analyzing this event. It was very hard to go there because you are in a crisis zone. So between South Georgia and Chechnya, you all know that it's very problematic to go there. It's dangerous. We had to have bodyguards all the time. So it's very difficult to do research or to monitor glaciers in such crisis zones. A second example of that, a well-known example, is the Siachen Glacier here. It's a glacier in the Kashmir, and if you zoom in Google, you see that the line between the Pakistan-controlled Kashmir, so Pakistan itself is a problematic zone, as you know, but this is a line between the Pakistan-controlled Kashmir and the India-controlled Kashmir, and even in Google, this line ends here, because it's totally open where the boundary lies. And actually, this glacier is much disputed, and this glacier is known as the highest battlefield on Earth. So no way to do glacier monitoring from ground in such areas. A third good reason to do glacier monitoring from space, it's simply the huge number of glaciers. There are many 100,000 glaciers on Earth. There's no way to do it by terrestrial surveying and so on, to hike to each glacier. So the only way is really from space, where you have the large-scale view. And it's not only that so many glaciers, some are huge, so it would be not possible to do anything from the ground. So this is an ice cap in the Canadian Arctic, for example. Here you see the scale. Or the largest ice mass on Earth, Antarctic ice shield. It's not possible to cover the entire ice sheet in, on ground. So you need remote sensing methods. And a fourth good reason to do that, to do glacier monitoring from space, it's a bit special, but some countries have lack of funding for glacier monitoring, so simply they have no people doing that. There might be unstable political or at least unstable administrative situations, so simply a certain administration is not existent, or they save money and save the money with this environmental agency, for instance. It could be the lack of expertise, which prevents people from a country to monitor their glaciers. It could be a different research focus. They have no research focus on glaciers. And often this leads to problems in maintaining long time series. Long time series are very important to really see changes of glaciers, to understand glacier change. So this is another reason to do glacier monitoring from space, because if we have a space instrument, we don't care about boundaries, we don't care about local administration. So it's one instrument monitoring all glaciers on the world with the same method. So that means remote sensing can overcome a lot of the problems, the four problem areas which I outlined. And now I come to 6 methods for glacier monitoring from space. So how is it done? So you know the good reasons to monitor glaciers, you know why to do it from space, and perhaps you want to know how is it done. One method is optical images. So this is an animation of repeat optical images from 85, 92, 98, 2003. This is Switzerland, between Zermatt would be somewhere here, and South Fee is actually somewhere here. So Swiss Alps. And you follow the movie, you see the glacier retreat very well. Also here, glacier retreats, hundreds of meters. So just by looking to time series of satellite images allows you to recognize glacier change. In that case, it's glacier retreat. Not all glaciers are retreating. You see also that a glacier here, for instance, is retreating just a little bit. Such time series of images can be also analyzed semi-automatically in a more quantitative way, not just looking at it, but really measuring. And I show you one method to do that. This leads us back to the glaciers in Bhutan, between Bhutan and Tibet Plateau. And I will focus on this rectangle in the next image. So this is how the glaciers would look from an airplane. So this is the visible range. This is what we are able to see. This is how the glaciers look in the infrared. We are not able to see that. So obviously, a very big difference. Glaciers and snow are dark in the infrared, but very bright, as you know, in the visible. If you do simply a division, as you divide two numbers, you can divide two images, and this is the result. If I divide this image by this image, I get this image. So you almost directly have the glacier areas. You can do a so-called raster to vector conversion. So it means an algorithm finds the transitions from glacier to no glacier, and these are outlined in red now. You also see that this method works mostly very well It includes a frozen lake, which is actually correct because a frozen lake is glacier. It's not what we want, so this has to be corrected, but in principle, the method works pretty well. The reason for that is that the reflection of snow and ice is very high in the visible, so the visible wavelengths go from here to here. This is the, from here on, it's infrared, which we cannot see. So even dirty ice, dirty glacier ice, fern or snow have very high reflections in the visible and very low reflections in the shortwave infrared. The curve in the background, by the way, is the atmospheric transmission. So wherever this curve is high, a satellite sensor is able to see through the atmosphere. Wherever this curve is low, a satellite sensor, nor we, would be able to see through the atmosphere. So that's the reason why satellite sensors are sensitive or have sensors in these so-called atmospheric windows. It would make no sense to measure here because we won't see the Earth. It would make sense for atmospheric research, but not for Earth observation. So this is the entire image from before, classified with this division method. If I go forward and back, you see that it works pretty well in most regions. However, you see also that the debris-covered glaciers, it's mostly the lower part of the glaciers, is not captured. The reason is that these glacier parts are covered by debris. It's not anymore ice, which is visible. So this also makes sense and has to be corrected. Meanwhile, such methods are applied to a number of regions worldwide. One of the first ones were the Swiss Alps, where I kind of grew up scientifically, by the way. So you see, and this axis, the glacier size. So these are the very small glaciers and the larger glaciers. And this is the loss of glacier area from 0. This would mean no change to up to 100% between 73 and 2000. You see that a number of glaciers totally disappeared, especially the smaller ones. You also see that the percentage area change is smaller for the bigger glaciers. This is obvious to some extent, but also see the big scatter. So it's not at all that all glaciers behave equally. So some might stay stable in the same size, where others totally disappear. So it depends a lot on local conditions. So with the method I showed you right now, it's possible, and this is underway, to map all glaciers worldwide. So this is the aim of 2 projects, GLIMS, Global Land as Measurement from Space project, and ESA project called Globe Glacier. These 2 projects aim really at mapping all glaciers worldwide using these technologies. The next step would be to understand how glacier mass changes. So these methods go for the area change. And for a number of applications, the area change is important. But the glacier mass would really tell us about the impact of climate change. This is Arlish Glacier in the Swiss Alps, in a photo from the International Space Station. The longest glacier in the Alps, European Alps. This is an elevation model from the Swiss Mapping Agency, and the glaciers are marked in blue. And this is a reconstructed elevation model from 1850, so the end of the Little Ice Age. And if I go forth and back, you see the mass change. So the 1850 elevation model cannot be measured because the time is gone. But it was reconstructed mainly from the moraines. But we have also some modern methods to measure elevation changes, thickness changes on glaciers, and to estimate the volume change of glaciers. And one method is satellite stereo. Some satellites are able to see not only downwards, so the so-called nadir, but they also have a back-looking or forward-looking camera, like that. So they take 2 images of the same spot, 2 stereo images. This is an example from Svalbard, Norwegian Arctic. This is the nadir image of the ASTER sensor, so nadir image. You see 3 rectangles, which I marked for comparison. This would be the backward image, so the image taken in backward direction. And if I go forward back, you see that the coastline, this is the coastline here and here, and points at the coastline stay constant, they do not move. But the higher a point or a mountain is, the stronger is the distortion between the nadir and the backlooking. This is a perspective distortion. And the idea is now to measure this distortion between the nadir and the backward. If you can measure that all over the image, you have something like the terrain elevation over the whole area, a so-called digital terrain elevation model, terrain or elevation model. So this satellite stereo. The advantage of optical stereo satellites is that you have images at the same time as you have elevations. So you can do fly-throughs or drape over. So this is a Aster satellite image of New Zealand, Mount Cook, Tasman Glacier, largest glacier on New Zealand. And from the stereo images, I created the elevation model, and then the satellite image was draped over this elevation model. This is only possible with this method. Another example is elevation changes. So we go back to Svalbard. These two ice caps here. This is how they look. And these are the elevation changes from the 70s to 2003, I think, derived from satellite stereo. This was the 2003 elevation model and an old map. And as for many glaciers, at the glacier tongue, the glacier lost about 90 to nearly 100 meters of ice thickness. In the upper parts, it's fairly constant, perhaps even a slight increase in elevation. So this is a typical application of this satellite stereo to derive glacier thickness changes, and if you cover an entire glacier, you can estimate the volume change of a glacier. The volume change of glacier is, for instance, the parameter which impacts water resource. This is the water resource in dry areas, the ice contained in the glaciers. A third method is to measure glacier flow. Glacier flow is also very important parameter, because glacier flow is responsible that ice and snow, which accumulates in the upper regions, accumulation regions of a glacier to the lower regions, this ice has to flow. This is a transport mechanism which guarantees the balance of a glacier. So glacier flow is important to know, and it's also important to know if the glacier flow changes drastically. And the method is to take repeat optical images to co-register them accurately so they fit together very well. And then you can overlay the two, and you see the glacier flow, I hope so. So these are images from January 2001 and November 2001, so nearly 1 year. This is the first one, second one. And you can see the glacier flow, but using image correlation methods. So algorithms can really check for point by point, and measure where's the corresponding crevasse in that case in the other image. And doing that, you get full so-called flow fields of glaciers. This is again rotated, but the same glacier that you saw before. So you can measure a large number of flow vectors. Actually, the highest speeds you saw in the animation before is 200 meters per year, quite fast. Then the speed decreases towards the glacier tongue. So this can be done for a large number of glaciers worldwide using repeat optical imagery. Great, all solved. So we can measure the aerial extent of glaciers, we can measure the volume change of glaciers, we can measure speed. Wait a moment, we have a problem. This is how the area looks in this image, but usually it looks like that. We are in monsoon region or partly monsoon, and this applies for many regions of the world, that when you take optical images from space and from ground, very often it looks like that. Okay, we have a problem. We have a second problem. This is this one. This could be an image over Svalbard or Antarctica in the polar winter. Second problem. The solution for these problems is radar. Radar penetrates through clouds, and radar is an active sensor, not like the optical sensors before, which relied on the sun as illumination source. Radar sensors they are active sensors. They send out a radar signal which is reflected to the sensor. And the method which is used to get images is called synthetic aperture radar. You know radar from the police, which measures your speed, but they have a point measurement, but we want images. So we use a different technique. It's called synthetic aperture radar. This is an optical image from the peninsula in Svalbard, which you saw before when I showed you the nadir and back-looking distortion. This is an optical image, like as you will see sometimes from space. This is the radar image. At the first glance, it looks a bit strange. It's much harder to recognize glaciers. The big ones, perhaps possible, but the small ones here, it would not be possible to map these glaciers from a radar image. Here you see, zoom in, the big glacier here, Kronebrain, fast-flowing glacier. Would be recognizable, but also here, the transition between the bedrock and the glacier, hard to map from radar images. Also here, very hard. So the technique which is often used for that is to take repeat images. So this is the first image is a springtime, or actually a winter image, February. This is an image from June. This is an image from September, late summer. If you combine, in none of these images, you would be able to really map the glaciers. But snow and ice have a very specific change signature. They change differently than the bedrock, for instance. If you combine all three, you get an image like that, which still is not perfect to map glaciers, but even the small ones, it's much easier to map the glaciers in such a so-called multi-temporal color composite. Actually, the yellow areas here indicate that we have different changes of ice and snow or different type of ice and snow in the upper parts of the glacier. It's actually a drier snow, no melt. A fifth method is SAR interferometry. For that, we take radar images, but we take two from the same spot. And radar is actually a distance measurement. Like the police, which measures your speed, they measure the difference from the measuring instrument to your car several times and estimate the speed from that. So if we have two radar images which contain the distance to the ground, we have a distance from the sensor to this spot and a distance from this sensor. It would be the same sensor often, but just another time to the same spot. And the difference of this distance is actually the measurement which is taken to, perhaps I should go back. And actually this difference here depends on the imaging geometry, where are the satellites, but it depends also on the topography. If the elevation of this point would be different, then this distance difference would also be different. So, and this is a big ice cap in Svalbard again, Spitsbergen, so-called Eisfauna. And these color cycles are the distance differences, which I showed you before. So the red arrow here, if I display the distance difference for each point, I get a picture like that. This is very close to contour lines, so I can use that to estimate the topography of this ice cap. There's one small problem. If I zoom in here and actually overlay the real contour lines, you see it's quite parallel here. So the interferogram, these are these fringes, these color cycles, interferogram, match quite well here and here and here, the contour lines, but not here. Here's an offset. This is due to glacier flow. When the glacier flows in between the two acquisition times, it creates a topographic signal, which is actually not a topographic signal. But if I take more than two radar images and do more than two interferograms, I can also estimate this glacier speed. So at the very end, I get the topography and the glacier speed. So the glacier speed would be the deformation of the topography in the interferograms. So this is SAR interferometry. Very well known for many glaciological applications, but also for landslides, slow mass movements, like settlement of cities due to groundwater outtake and so on. It's always the same technique. And the last technique I'm talking about is satellite altimetry. If you have a satellite and know from monitoring from the ground stations how high the satellite is, and if the satellite measures the distance from the satellite to the ground by either a radar signal like the police uses or a laser signal, so I have the yellow distance, I know the blue one, I can calculate the red one, which is topography, so the elevation of ground. Radar altimeters, the ESAR runs several ones, are used to measure large bodies like Greenland or Antarctica, or even elevation changes on Greenland or Antarctica. The resolution of these radar altimeters is quite coarse, so several kilometers is one footprint, so it's very hard to determine fine details. Another altimeter, it's a NASA altimeter, works with laser. And actually, I show you this glacier tongue as an example here. These are the footprints of the laser instrument. It's an ISAT glass instrument. Over this glacier tongue here, this is the glacier tongue. And the footprints are on scale. So each dot is 70 meters. This is the footprint of the laser. And the distance between footprints is 170 meters. And these are actually 4 tracks, 4 repeat tracks, 4 times 4 colors. If I look to a profile going from the sea here to up to the mountains here, it looks like that. The circles here are the 4 ground tracks of the laser instrument. The dark line here is the elevation model from optical stereo I showed you before. Fits quite well. Here's a mistake in the optical elevation model, but else it fits quite well. And the red dots, bold dots, are the contour lines from the 1970 map, topographic map. So actually, a contour line would go in the image or out the image here. So here you see the elevation change of close to 100 meters, which I was referring to before. So you see it very well between old elevation models, so contour line maps, and new instruments like a laser altimeter or an optical stereo instrument. Okay. So I'm coming to the end of my talk. I gave you 5 good reasons to monitor glaciers. For instance, global sea level rise, glaciers as water resource, glaciers as natural hazard. I gave you 4 good reasons to do that from space. It has mostly to do with accessibility and to have a globally uniform measurement system from space. And I gave you 6 methods, the most established methods for glacier monitoring from space. All these points and some more are part of an educational module which ESA builds up with EduSpace. We were developing a glacier module which should be online during this year, I hope. This module contains 1 chapter about introduction to glaciers, where the principles of glaciers are explained. A second chapter describes remote sensing methods for glaciers. Then there are a number of exercises, and this afternoon you will be able to do these exercises, some of these exercises if you want. So one exercise, for instance, explores the optical properties of snow and ice in different wavelengths. One exercise explores the response of radar response of snow and ice. You have seen this image before. One exercise goes for glacier mapping, so manual glacier mapping, perhaps also automatic glacier mapping. One exercise goes for glacier change detection to see how glaciers change, to measure that from space. One exercise goes on satellite stereo to measure terrain elevations from a nadir and a back-looking image. And one exercise goes on flow speed measurement. So you see some crevasses which have been digitized. And you see the same digitized crevasses here, but the crevasses have moved. So by that way, you can measure the glacier speed. And all these exercises use the LeoWorks software, which you might know, or at least you know it this afternoon. This educational software by ESA. Yeah, so this will be a topic for this afternoon. And finally, the EduSpace Glacier module contains also a Google Earth KMail file, which contains a number of typical glaciers and a short description of these glaciers and the satellite image, which is different from the one in Google. It contains a selection of glacier disasters and description of these glacier disasters and satellite imagery describing in more detail the glacier disasters, in that case the glaciate outburst. And the Google Earth file also contains the locations for all examples in the glacier module. So you can actually also use the Google Earth file as an entrance. So you can just look, OK, cool glacier, in which exercise is it used? With that, I'm at the end, and I hope that you got some inspirations for your everyday work in classroom. Thanks a lot.